All right, here we are. Okay, so let's go ahead and go to the current slide. There we are. Power conversions. Okay, convert to horsepower. What you do is you take your watts and you multiply it by this 0.00134. I think you'll have to do that on your in your lab, right? So power is 328 watts, 0.00134. Okay, what? And I just kind of realized today this is taking a while. Like I said, I'm teaching you about 4 weeks of 210 in a very abridged, condensed version. And so I'm just going to get the pre-lab done today, and we'll do the lab part tomorrow, right? Um, or maybe even we'll do the lab part probably on Monday is what we'll do, okay? So power is 0.4 horsepower. So you take 328 watts times 0.4 horsepower. This was, compare the output of the rock climber with the world's fastest car. Look at that, 1,183 horsepower. That's a lot of horsepower. All right. So energy. Energy comes in two forms. Kinetic energy of motion, which we talked about, potential energy, okay, that is stored up, for example, in a battery or spring. And the equation for kinetic energy is 1/2 mv squared, where m is the mass of the object and v equals the speed of the object. Okay? So that's the kinetic energy. And if you take the amount of work done, if you're speeding something up and you're pushing on it and it's accelerating and getting faster, then the amount of work done can be calculated by the change in its kinetic energy. If it started from rest, the velocity would be 0, and then its final velocity is 1/2 mv squared. Okay, and you can figure out the kinetic energy that it expended. Okay, the world's fastest human is Usain Bolt. In Jamaica, he ran in 9.58 seconds in Germany, in Berlin, in 2009. His mass at the time was 95 kilograms. His average speed is 10.4 seconds. Calculate his kinetic energy for the world record run. All right? So I'm going to show you what writing this out looks like in calculating his energy. So here we go. Kinetic energy is equal to 1/2 mv squared. So you take 1/2. Now, how do you do 1/2 on your calculator? I usually do 0.5. You have 0.5 times 95 times 10.4 times 10.4 if you don't have the squared button. That's 5,038 joules. Okay? The Brabus car, what's the kinetic energy when it's traveling at a top speed? 270 miles per hour, where you'd have to convert that. 270 miles per hour is about 120 meters per second. I'm not going to bother with the calculation on that right now. That's not important for us. Okay? And then we take kinetic energy, 1/2 mv squared, about 8.8 megajoules. This is 5 kilojoules, 8 megajoules, about 1,000 times more kinetic energy. Why? Much faster, much more massive. But you get all your energy in the speed because it's the squared item. Okay, potential energy. There are many types of potential energy, but we're just going to look at the gravitational, which I've already talked about, where the potential energy is equal to mgh. Mass of the object, g, is equal to 9.8 meters per second squared near the surface of the Earth. Potential energy example. The height of a platform diver, okay, is 10 meters above the water. Calculate the potential energy of a diver standing on the platform where he has a mass of 81.8 kilograms. Well, that's pretty easy, because what did we say it was? Mass times g times 9.8. I already kind of did that in the beginning. It's all mushed together. It's kind of repeating. So that's 8,016 joules. Okay, and we'll talk about, well, ramps help us do work because what we do is force times distance, the amount of force times the distance, assume no friction. How much work did they do? Okay, all right, so they went up a 3-meter long ramp, so, and the force is going parallel to it, so they went 2.5 times 9.8 times, but they only raised it. They just took it up 1 meter high. So the work that they did was the kinetic energy, was the potential energy they raised it, which is mgh times 1 meter, 2,450 joules. But the force they pushed was not equal to mg. okay, what was the force that they used to push it? Well, they went the force times the distance is equal to the energy, divide the 3 meters of, they only used 817 newtons of force. The force, but the actual to lift the thing 1 meter high would take 2,450 newtons. So that the ramp, due to it's a 1-to-3 ratio there to the height, that 1-to-3 ratio means that it lowered the weight of that thing by a third. Okay, lowered the weight of the thing by a third. That's why if you can get a long enough ramp, a 10-meter long ramp, to lift something really heavy, if you can just push it up there for 10 meters, you can save a lot of energy. I think that's it. Yeah, that was it. All right, so now, so we finished out the slide. So now what I'd like to do is let's just go look at, now I know I didn't work a bunch of things there, but let's go look at the pre-lab. All right, let's take a look at the pre-lab.